Hi everyone, and welcome to Lecture 1B, the Prelude chapter of your textbook, Welcome to Earth and Space Science. Typically, these lectures will be 5 to 15 slides long and 5 to 15 minutes long, so as to keep your undivided attention in digestible pieces. They are mostly comprised of images and texts from the textbook and augmented with images and text of my own that embody my professional ideas as a geoscientist and things I think that you should know that the textbook doesn't mention. So today we're going to answer the question, what is Earth, space, and space science? This question that you were asked in the lecture activity for Lecture 1A. Your textbook introduces what Earth scientists study through the example of Antarctica, and it's a great example. They have a story of some researchers flying in a plane over the Antarctic ice sheets and discussing what opportunities there are for studying the Earth system in this location. So if we were just to take a look at a picture of a map of Antarctica, we'd notice that it's comprised of many components. For example, the South Pole and the West Antarctic and East Antarctic ice sheets, which are divided by the Transantarctic Mountains. These two ice sheets actually sit atop two different pieces of the Antarctic continent as glaciers, and if we're able to see the edges of the continent and the coastline, we see portions where that ice sheet has melted away. So geologic fieldwork in Antarctica can unlock many mysteries of this ice-bound continent. So people study ice loss, ice accumulation. They study the rocks there to figure out what types of rocks and what resources exist, where the continent has been in the past, as well as all of the important ocean circulation and atmospheric circulation that goes on there and the life that lives there. So if we wanted to define Earth science and its components, we would say Earth science is the systematic analysis of natural phenomena based on observation, experiment, and calculation. And in this textbook, we have defined Earth science as including the disciplines of geology, oceanography, atmospheric science, and space science. It's important to note that these terms go in and out of vogue. Of course, Earth doesn't really include space science, but for our purposes, we're going to let that slide. So we will discuss what is geoscience. Geoscience is the study of our planet with a focus on the materials that compose it, phenomena that change it, and its long-term history. Ocean science is the study of water and life in the oceans, as well as the way in which ocean water moves and interacts with land and air. So these two photos show a geologist studying a rock face. It looks like they have an instrument in their hands to measure the orientation of the rocks, which we actually call a compass. This is a special type of geologist compass that allows us to determine the relationships between different rocks in the field on foot. And on the right, we've got some oceanographers deploying instruments to measure ocean water. They're probably measuring temperature, salinity, depth and pressure, as well as various other things. Atmospheric science is the study of the air layer that surrounds the Earth. And we can divide up atmospheric science into two subdisciplines, which are meteorology, focuses on weather at a given place in time, or atmospheric conditions at a given place in time, or climate science, which focuses on weather patterns over a period of time for specific regions or the entire Earth. Space science is the study of planets, stars, and other objects and phenomena in the universe. So these pictures show an atmospheric scientist monitoring the atmosphere from their office, and a picture on the right of a view of space from the International Space Station. We can divide the Earth system into different spheres that encompass these ways that we determine the earth science disciplines. So we have the geosphere, which includes all solid material on Earth, so the solid Earth to the core. The hydrosphere, which includes all water on Earth in liquid and solid forms, so that would be water in the oceans, rivers, on ice sheets, and in our bodies. The cryosphere, which is a subsphere of the hydrosphere, which only includes frozen components of the hydrosphere. The atmosphere, which includes all gases surrounding the Earth. And the biosphere, which is all living organisms on Earth. So I like this picture. I think they chose it for your textbook because it shows all of these different spheres in one photo, and the fact that they all interact with one another on a daily basis. We've got living material, we've got rocks, we've got liquid water, an atmosphere, all interacting with one another. We don't discuss this too much in our textbook, but it's important to think about how the Earth system and how these different spheres get their energy. And the answers are there's internal energy, gravity, and external energy. So if you want to think about internal energy, it's energy that was created when the Earth formed from compression. So deep within the Earth, it's very hot and it's very, very high pressure. And that's a result of the original collisions and amalgamation of Earth. And secondly, we have radioactive decay deep within Earth that's also producing heat. And those together allow form Earth's core and some of the energy that's produced from it, which we'll talk later. Then there's gravity, attraction between masses, of course, on Earth and between planetary bodies like Earth and the Moon or Earth and the Sun that are important energy sources. And then an external energy from the Sun, solar radiation, which is what drives all life on Earth. It's important to think about the universe and Earth in terms of time because they're both very old. So if we define cosmologic time, which is actually intervals related to the age of the universe, which is 13.8 billion years old. Geologic time is intervals related to the age of the Earth, which is only a fraction of the age of the universe, and Earth is around 4.5 billion years old. So on the left, what we have are called the cosmologic timescale and the geologic timescale. You'll notice that the geologic timescale is divided into different periods, which are named of eons and eras, and these names often have some meaning in terms of the history of the Earth. They are transitionary periods, so to speak. And one way to think about how do we study Earth's spheres? How are they related? One way is to think that they are connected through something called plate tectonic theory, where continents and ocean basins sit atop the interior of the Earth and slide across it. We'll talk more about plate tectonics in the next chapter. So we want to ask ourselves in this lecture as well, how is science done? There is the scientific method, which we've learned about in school throughout our lives, where we recognize a problem, propose a hypothesis, test the hypothesis, establish a theory, and define scientific laws. I want to note to you all that this is an idealized version of the scientific method. It's not often reality, doesn't reflect the day-to-day life of scientists, but rather the long-term achievements of science or progression of science over decades and centuries and millennia. The reason is because hypotheses of individuals almost never become theories or laws, and if results and conclusions are valid, typically they just become publications in scientific journals. So one example of this is that there's only about 20 laws for natural sciences that aren't physics, chemistry, or math, and in 2009 there were about 50 million articles published in existence. So that would mean 1 out of every article, has ideas that eventually make their way into becoming some sort of theory or law. The more realistic version of the scientific method that I think is important to share with you all, and is more personal for me and for all individuals that I know, is typically goes like this. You recognize a curiosity, then conduct a literature review to learn from others who have done similar work. Then you propose a study to get funded, conduct the study, analyze the data, draft and revise a manuscript with co-authors, publish the study if your results are valid and useful and interesting, and then begin new studies building off previous expertise and mistakes. So on the left, we have a more simplified version of how science is done. You start with exploration, then you test your idea, you get feedback, and often you continue this loop until feedback has said, yes, you have a beneficial, you've produced something beneficial, and it results in a good outcome. So I bring this up because I want to explain to you how science works and how scientists work, rather than give you this idea, this sort of idealized version of science. We also want to talk as Earth and space scientists. How exactly do they conduct their work? Well, they conduct research, which is the search to understand natural phenomena through observation, experimentation, and calculation. And we can divide up scientists into 3 different types: field scientists, lab scientists, and computational scientists. Field scientists do their work in the natural environment, aka outside or the field. So geoscientists may sample rocks from outcrops, or atmospheric scientists may fly into storms. Oceanographers may go on ships into the ocean. Laboratory scientists do analyses in the lab, and this is rather self-explanatory, but they provide an opportunity to carry out controlled experiments. And then finally, there's computational scientists who develop models to simulate conditions of natural phenomena. And there can be computer models like the one we have on the bottom right of a thunderstorm, or physical models. You would imagine creating a physical model of a wave chamber where you've got this bathtub where you're producing waves from some mechanical engine. So often scientists in real life do all 3 of these things. They go to the field, they study in the lab, they do their analyses, and develop computer models. At least Earth and space scientists do. And I would say that computational science is sort of a higher order level. If you can get to that point where you're developing successful models, then you are being a successful scientist. So, as a part of your lecture activity, I'd like to ask you, if you had to work as a geoscientist, ocean scientist, atmospheric scientist, or space scientist, which would you choose and why? And if you had to work as a field scientist, lab scientist, or modeler, which would you choose and why? Also, use only your mind as a resource in this case. Write a minimum of 5 sentences, either on your computer or paper, and then we will turn this in through Canvas. This ends Lecture 1B.